Hi, Chuck Dieter at the Headwaters Science Center with a little bite of science for you. So, take a look. Got a tank here with some water in it, just ordinary tap water right out of the faucet. And we're going to run a little experiment here. And while we're doing this, I hope I can encourage you to make some predictions, kind of think in your mind what's going to happen when we run this thing. So, the tap water is at about 62 degrees Fahrenheit. It's about the temperature of that. And I've got 3 samples that are, well, I took the water right out of this tank, but they're a little bit different because I did something to them. Now, the red sample is, as I said, water right out of this tank, but I heated it up in the microwave. So it went up to, actually it went up to boiling. So it's been in that flask for a little while. It's probably cooled down a little bit now, but it's still well above the temperature of the water in the tank. The one in the middle, the blue one, it's kind of dark, but you can tell, you're going to be able to tell it's blue, is cold. I put some ice cubes in it and cooled that down to about 42 degrees Fahrenheit. Now, the green one is the same temperature as the water in the tank. The only thing I did with that is I added a few grams of salt to it. What we're going to do, of course, is we're going to put these in the tank, and I'm going to remove the corks, and we'll see what happens. Got any predictions? So removing the cork, the one with the hot water in it. I see something starting to happen. And the hot water is coming out of the flask, and it's not really mixing with the water in the tank. It's going up in a column to the surface, and then spreading out on the surface. Let's see if the cold water behaves the same way. Nope. I see a little bit of blue in the water from when I took the cork out. I dragged a little cold water out with it, but not doing the same thing. Wonder what will happen if I tip it a little bit. Pretty much the opposite. It's staying together. It's not dispersing throughout the water in the tank, but it's headed for the bottom. Looks like I'm pouring syrup or molasses into the water. Now the green bottle. Same temperature as the water in the tank. Has a little salt dissolved in it. Didn't come out like the red water. Staying in the bottle and in the flask. And when I tip it a little bit, it flows out fast and spreads out in the layer on the bottom of the tank. Now, I don't know whether you can see it on camera, but from my perspective, I can see that the green water, the salty water, is actually flowing under the blue water, the cold water. So why'd that happen? Why the differences between the 3? Okay, now there are 3 basic scientific ideas behind what we just saw. And there are probably some other things we could talk about too, but the 3 main ones are what we're going to talk about, and they're not just things that showed up in some experiment we came up with. They're things that affect our lives, things that affect the real world around us every single day, and the real world inside us every single day. They are the idea of density, the idea of solutions, which is maybe not what you think, and the unique properties of water, one particular unique properties of the water molecule. And that's responsible for this and responsible for all kinds of things in your daily life. Okay, before we get into density, let's talk about a few basic scientific ideas. I know this is review for pretty much everybody. You probably already know this, but review is always good. All right? Okay, scientific idea number one is all the stuff in the universe, all the matter in the universe, is made up of little tiny, tiny particles. We're talking measured in 10 millionths of millimeters. If the substance is a pure substance, an element, then those particles are atoms. Well, most substances are compounds, they're combinations of elements, and they're made up of clumps of atoms called molecules. That's scientific idea number one. Scientific idea number two, those molecules are never still. They're always bouncing around, always bumping into each other. Now let's, for example, use these ping pong balls to model, it's going to say these represent molecules. They're never still. They're always bouncing around. Always knocking into each other. Now, that's scientific idea number two. Scientific idea number three is that if the molecules are bouncing faster and farther apart, then you say that the substance is getting warmer. If the molecules start bouncing slower and closer together, it's getting colder. Simple. Warmer. Colder. Warmer. Colder. Okay. Now, let's imagine that these ping pong balls are water molecules. Like the water molecules in our experiment. Let's just imagine that they are the water molecules in our experiment. See these tape marks on the side? We're going to imagine that if they're bouncing around about that level, about up to the tape mark here, that's the temperature of the water in the tank. The temperature of the water in the hot flask would bounce up to about the top of the tub. Like that. The temperature of the water in the cold flask would only bounce about that high to the first tape mark. There. Pretty easy illustration of density, right? You got the same number of molecules, the same amount of mass of stuff there, but if it's bouncing up this high, like in the hot flask, that same amount of matter is occupying a lot more space. They're farther apart. If they're bouncing like in the cold flask, the same amount of matter. See that? I don't know if I'm getting it right on the camera. Same amount of matter, same number of molecules, but they're occupying a smaller space. They're tighter together. So, if you measure out a milliliter of water and you raise its temperature to, well, if you have a hot water, you measure the hot water out, a milliliter of the hot water out, the molecules are going to be farther apart, so water at this temperature is going to weigh a little less than a milliliter of water at that temperature. By the same token, if you measure a milliliter of water at this temperature, it's going to weigh a little bit more than the water at that temperature. It's denser. So, if the water is at this level, the cold water, it's going to be denser than the water here at room temperature, the water in the tank. So when it pours out into that water, it's going to sink right through it. Just like a stone would be denser than the water in the tank. You put a stone in the tank, it would sink right to the bottom. And the water in the hot flask is going to be less dense than the water in the tank. It's going to float right through it. It's less dense, just like a piece of wood would float to the top. Pretty basic idea, huh? So that explains why the red water went to the top of the tank, why the blue water went to the bottom of the tank. But then what happened with the third flask, the one that was green? Now the water in the green flask was the same temperature as the water in the tank, but it had something dissolved in it. we're going to say that it had some salt dissolved in it. We're going to say that these blue ping pong balls represent salt molecules. And what happened was they dissolved. The water in the tank broke up the salt crystals into individual molecules and actually pulled some of the molecules apart, and they fit in between the water molecules. So it didn't increase the volume of the liquid, but there's more mass in it. So it can be only that warm, but much more dense than the water itself, because it has more matter dissolved in it, more matter packed in between the water molecules. That's why it poured straight to the bottom and formed a layer that was even denser than the cold water. Basic idea. That's how we got our results. Let's imagine that this is water, and every one of these is a model of a water molecule. And you probably know the chemical formula for water, H2O. That means 2 atoms of hydrogen, the H's, attached to 1 atom of oxygen, the O. Now, what happens when 2 atoms of hydrogen attached to 1 atom of oxygen is a net negative charge down here and a net positive charge up here. And as we all know, positive and negative charges attract each other. So in water, they're always pulling on each other. Negative and positive are always pulling together. Always pulling together. And that means that this is a cohesive liquid. That's one of the unique properties of water, cohesion. It tends to hold itself together. The water molecules cohere. Now, then you put in some salt. Here's a salt crystal. Salt is a combination of sodium and chlorine. Let's say that this is a sodium molecule, a sodium atom, and that's a chlorine atom. But what happens when it gets into the water is that the positive and negative charges on the water molecule can pull, no matter what charge it is, whether it's positive or negative, in the salt crystal, it can pull on it, and it pulls the molecules, pulls the crystal apart and the molecules apart, so that individual atoms are floating around in between the molecules of water, and they get distributed evenly throughout, I don't know if I'm doing this evenly, but that's the idea, throughout the water, producing a solution, which is not a new substance necessarily. It kind of acts like a substance. There's no chemical reaction involved. But, of course, if it occupies the same amount of space but has more matter in it, it's more dense. And that's what we saw in our experiment. Because these things are all pulling together, when a faster moving, warmer molecule of water from a warmer water mass hits one of these and starts to speed it up, well, the others kind of pull against it and pull it back into the mass of cold water and tend to make it go at the same speed as the rest of them. So it takes a long time for water to change its temperature, either getting it warmer or getting it colder, because of that attraction for water molecule to water molecule. Okay, that's the basic idea, 3 basic ideas. Density, solutions, and the unique property of water, cohesion. Okay, this brings us down to one final question, which I think I can hear a few of you asking. Who cares? Why should I spend my valuable time thinking about density and solutions and water molecules? What does this have to do with me and my life? A lot. Constantly, there are huge masses of salt solutions, seawater, moving across the planet through the oceans, and they affect everything on the planet. They affect, well, all the life in all the oceans of the world. They affect the atmosphere, which affects things like climate, things like growing seasons and rainfall patterns, agriculture, how much food you get to eat, what kinds of food you get to eat, and how much it costs, weather events, things like hurricanes and droughts, and, icy roads in the wintertime, and how much it costs to keep those roads in good repair, and how much I have to shell out for heating and air conditioning. Just about everything on the planet is affected by those masses of water moving through the oceans. And to a large degree, they're moved by differences in density caused by differences in temperature and differences in the concentration of salt solution, seawater, and by the cohesion of water molecules. So if you're curious at all about that, you might say try looking up El Nino or La Nina. Try looking up, say the North Atlantic Drift. Here's a good one. Antarctic underwater waterfall. And going along with that, Antarctic brine. Fascinating subject. Oh, and you could also look up seasonal lake turnover. Lake turnover. Like this. That's enough of a bite for now. Food for thought.